All right, how'd you do with the quotient rule homework? I know we did some pretty tricky problems in the notes, but some of these problems in the homework kind of go back to the basics where you can actually just do the math. You can, in this case, take 3 over 24 and just reduce that to be 1 over 8. Now, the reason I reduced that to be reduce that first is because now I can actually do the cube root of each of these numbers, and the cube root of 1, well, of course, that equals 1, and the cube root of 8, as we've seen many times, that's 2. Now make sure you realize why the cube root of 8 is 2. That's because 2 times 2 times 2 equals 8. It's also because 2 cubed equals 8. But in the end, we're able to take out all of that 8. We're able to take out all of that 8 and just create the number 2. So we're not left with any root signs anymore. We're just left with 2. So yeah, don't split this up into be the square root of each of these. You can't do the square root of both of those. Instead, just do the math. Do the 162 divided by 2. Get 81. And really what you get is the square root of 81, which we've always known is equal to 9. Not the square root of 9, but just 9. Now, in a situation like this, it might be a good idea to bring this whole thing back together to be one radical. That is the root of 81 divided by 3. The reason that's a good idea is because when you get the number 27 under here, you can actually do the root of 27. Now, it's not the square root, it's the cube root. And it turns out that 27 has a perfect cube root. That would be the number 3. So again, all of 27 is able to come out as the number 3. You're not left with anything. It's because it's already a perfect number. Now, I don't really like my hint that I gave you here. I started the problem. I mean, what I really did was I split it up, something that you guys have done many times. So now that the problem's split up, we've got a radical in the denominator. Uh-oh, you can't have that, so you're going to have to multiply the top and bottom by some more denominator. Okay, the question again is, how much denominator do I need? Well, I need 4. How much do I have? Well, I have 1. So how much more do I need to multiply by? Well, I hope that you say you have to multiply by 3 more. That is 7 to the third. 7 to the third is what I have to multiply to the top and bottom. Now, when I multiply by 7 to the third, that gives me a total of 7 to the fourth, which was my goal. I want to get those 4s to cancel out. And if you already know that they're going to cancel out to be 7, then just change it to 7. But you do end up with something new in the top. You see 7 to the third. Well, that's 7 times 7 times 7. That's kind of a big number. That's 343. But what's going to happen is I can put that number with this x cubed. I can put this all together. And when I put it all together, I get 343 underneath with that x cubed. Now, don't do anything else. Don't try to divide 7 up here. One of the numbers is on the inside, one's on the outside. So we are all done. We start getting into problems with variables. When you have a variable, well, whether you have a variable or not, when you have a radical, you can split this radical, you can put it on the numerator and denominator. And again, this is a classic case of having a radical in the denominator. You're not allowed to have a radical in the denominator, so we want to multiply by some more x. How much more x? How much more? The answer is we want to multiply by 2 more. That's because we already have 1 and we're trying to get 3. So we multiply by 2 more. That is, we multiply by a radical of x squared. Now, the denominator cancels out. We've seen this a few times now. It just cancels out to be x. The numerator, well, it just all comes together. You get a root of x squared y squared. That's fine. You're done. Okay, it looks like that the only thing we really can do is split this up. You split it up, you end up with a root in the denominator. Yes, that's not good. You can't have a root in the denominator. But I'll tell you what, before we do anything with that, you kind of should notice that this x10, there's a lot of x right there, and some of that x can come out. In fact, a lot of that x can come out. What's the highest amount of x that's divisible by this 3? Well, you should be saying x9. So I can kind of rethink of this as x9x so that we can pull this 9 out, just like we did in the last lesson. Now remember, when you take that x9 out, it's going to divide by the 3. It's going to divide by the 3, which actually leaves you with 3. So we're doing a little bit of quick work ahead of time here. We're pulling out that x9. It's leaving us with x3. It's also leaving an x behind. Now let's talk about this denominator. And as we've said many times, you can't have a radical in the denominator. So we're going to have to multiply by some more 4. Some more 4. How about 4 squared? So we multiply top and bottom by 4 squared. And we're going to, of course, be able to do some canceling down here. The canceling is going to leave us with just 4 in the bottom. But it's also got some surprises in the top. The 4 squared is actually the number 16, which I'm going to be able to put under the radical that is on the numerator. We're going to have a 16 that's under there along with this x. Now that x I just wrote down is that circled x. Now, it's a pretty good job, but it's actually not done yet. It's not done yet because if you look a little more closely, this 16 has a number inside of it, a perfect number inside of it that's able to come out. And it's the number 8. You can think of 16 as 8 times 2, and you can take that 8 out. And when that 8 comes out, it's going to turn into a 2. So I split up 16, I take the 8 out, it turns into a 2, because that's the root of 8. And we're left with this 2, this x underneath here, and, well, we've had this 4 in the denominator for a little while. Done yet? Well, not until you realize that you can actually divide those numbers. You can divide those numbers and end up with even less. Now we're done. As long as you realize that the final answer is x cubed, the root of 2x, all divided by 2. All right, one last problem. As we've done multiple times, split it up. That's because, well, actually, you know what? You could split it up, but I was just noticing here, why wouldn't you do some math? I mean, if you can divide, if you can make the number smaller, you should do that first. So I'll tell you what, I'm going to change my plans here and divide so that I end up with just less numbers. Now, I'm still going to need to split this up, but whether you realize or not, I actually did myself a favor by doing some simpler math before we deal with the complex. Now, the complex is to realize that, there's a radical in the denominator. And, you might say, well, what am I going to multiply by? Well, you realize you actually can multiply by just a little bit more x so that you can make that x to the 5 turn into an x to the 6. Do you realize that if you make this turn into an x to the 6, which a 5 and a 1 would give you 6, that is going to cancel nicely with this 3. So I'm going to multiply the top and bottom by a root x, because that's going to give me x to the 6. And again, an x to the 6 in the bottom is going to cancel nicely with that 3. Just so you know, in the top, you're going to be left with a 2x, a root 2x. And now we can do the business of canceling with that x6 that we've been talking about. Remember, when you cancel these numbers, you actually divide them. And when you divide them, you get x squared. So we're going to get the root of 2x, the root of the cube root of 2x, all over x squared.